So today we're going to be tackling the succeeding tank problem where we have three tanks in which the inflow that we have an initial steady state with an inflow of 0.1 meters cubed per second. So let's go ahead and just write Q in 0.1 meters cubed per second. And then the three tanks have a common drainage hole area of 0.01 meters squared. So we can go write this down as AD2 which is all equal to 0.01 meters squared. And the cross-sectional areas are that, respectively. So we could go AC1, which is the cross-sectional area of this tank, is equal to 1.0 meters squared. AC2 is equal to 0.5 meters squared. AC3 is equal to 2.0 meters squared. And for each one, we also have some height of the water level in the tank. So we can also label that. And with that, we can go ahead and start tackling this problem. So one more thing we might want to put in is that we have these flow rates going in and out of our tanks as a result of the fact that there is mass entering and exiting each of these tanks simultaneously. So we know that within this three tank system here, it's going to be at a steady state, as it says right there. And so with the steady state, we know that our change in height with respect to time is equal to 0. And that's going to be equal to the area of the first drainage hole. So times the velocity, and we know by doing our energy balance that our change in height over change in time is equal to 0, and our velocity for that is going to look something like that. So using this, we can go ahead and try and find our flow rates between each of the three tanks. So let's start deriving some differential equations for this. So the first thing we can look at here now is we have a definition for dH/dt here. So we could take a look at how we can relate that to our cross-sectional area and find the flow rates between it, right? So the cross-sectional area of 1 times the differential of height over time is going to be equal to basically Q in minus the Q out. However, we can rewrite the Q out to be the area of the first drainage hole times the square root of 2g times h to the 1/2. And that'll be for h1. And so this is going to be very similar for the other two tanks. So we have AC2 times dH2 dt over dt is going to be equal to, now our flow in is going to be this this velocity here. So Just going to rewrite that. And we're going to do the same thing for the second one, the drainage hole. And we're going to do the same thing for the third one. Going to derive each of these differential equations. And these are the first sets of differential equations we're going to use to go ahead and try and solve this problem. I am just now realizing I kind of made a mistake up here, so I'm going to try and fix that really quickly. So it is true that at a steady state, our change in height over time is going to be 0. However, that doesn't necessarily mean that the velocity there is going to equal 0, because that really wouldn't make any sense if nothing is moving. However, that means more so that the flow going in at steady state is going to be equal to what we had written before, which is the area of the drainage hole times 2g times h to the 1/2, which is why we use this inflow for each of these, and the outflow also represents that. So that's kind of why we use that, not necessarily because velocity equals 0. That's kind of impossible. So we have these equations which will relate our change in height over time to the in and outflow. However, we should probably also want to initialize our initial heights at the steady state. And that's going to look something like this. So if we were to find height 1, move over here a bit, that's going to be equal to the Q in at steady state squared times the area of the drainage hole squared times 2g. And this is going to look the same for each of the heights. So this is going to be Q in steady state squared, area of drainage hole 2 squared times 2g, and do the same thing for height 3. And so with these now, we have initialized the heights for each of the tanks at the initial steady state. Now, the last step in this entire process, and this seems probably pretty menial, but before we go ahead and simulate this in a Python environment, we're going to use the solve IVP function, and the solve IVP function requires us to isolate our differential term. So we're just going to rewrite these equations like that. So we're going to have something like dH1 over dt is going to equal the initial flow in, so Q in over AC1 minus area of the drainage hole 1, 2G, just rewriting out everything and then putting that over AC1. That's essentially what we're doing here. So go ahead and do the same thing for the second differential. So this time it's going to be ADH1 minus ADH2 square root of 2g times height 2 to the 1/2 power all over AC2. And now dH3 over dt equals ADH2 square root 2g h2 to the 1/2 all over AC3 now minus ADH3 square root of 2g to the 1/2 h3 1/2 all over AC3. With this, we are now ready to go ahead into our Python environment and go ahead and use solve IVP.integrate to go ahead and solve this tank problem. New day, same thing. Let's go ahead and get started coding. Now, before we go ahead and simulate what we want to simulate our tank issue here, that's the thing that we want to use the solve IVP function for. We have to go ahead and import a few things first. So we're going to import numpy as np. And then we're also going to take from the scipy integrate library, scipy.integrate. We're going to import solve IVP, and that's what's going to give us our individual value problem solution. And then also at the very end, we want to go ahead and graph this simulation out. So we're going to go ahead and import from, I believe it's plotly.subplots, import make subplots. And now we can go ahead, we can put in our put in the values that we'll use to go ahead and solve this problem. So now let's go ahead, let's start importing. So we're going to import gravity, of course. That's 9.81 meters per second squared. And we can also go ahead, we're going to import the initial flow in, so q in not, and that's going to be equal to 0.1 meters cubed. Whoa. It's going to be meters cubed per second. And we're also going to go ahead and increase this to 0.15 at some point. So just keep this on the side here to keep q in equal to 0.15 meters cubed per second. The next thing we can go ahead, let's take a look at our whiteboard again. So we can go ahead, we can give them the common drainage hole area. And the way we're going to do that, I'm going to call that area drainage hole. And we're going to create an array of values. So use np.array. And the reason we're doing that is because, yes, they're all the same 3 values. But since we want to go ahead and use these later on, we can just put these in an array and use those as we see fit. We can go ahead, put in our cross-sectional areas, which were 1.5 and 2. So AC1, AC2, AC3 equal to 1.0, 0.5, 2.0. And these are both in meters squared. And another thing we can put in here now is that initial height, our steady state height. And if you remember, that is the flow in at steady state squared over the area of the drainage hole squared times 2g. So let's go ahead and go height initial, height not. And that's going to be equal to q in initial squared. Put that inside. Divided by the area of the drainage hole squared times 2g. And that should give us each of the initial heights for each of the tanks, since this 80h here is going to give us the values of that array. So if we were to run that, we see we get the same 3 values for each of the tanks. So now with this, let's go ahead, write down our functions and use solve IVP to go ahead and get our values. So if we take a look at the whiteboard, we see that we have this equation for flow, and each of these values is basically a flow for the first tank, a flow for the second tank, a flow for the third tank. So let's go ahead, we're going to define our function, dHdt, and of course we're going to use our variables t and h. And we're going to calculate using Q1, Q2, Q3. And these are going to be equal to this equation that we have here for each height. So we'll go area of the drainage hole times, and this is going to be 2 times G times H, all to the 1/2 power or square rooted. Double check that. Yeah, that looks right to me. And then we want to return these equations for dHdt. So basically this first one here is Qn minus Q1. We're going to name this Q1 all over AC1. So what we can end up doing here is we'll go Qn minus Q1 over AC1, and then we'll do the same thing for the second hole, and we're going to go Q1 minus Q2 over AC2, and then just make this easier on us. Switch these around, make this the third cross-sectional area, Q2 minus Q3. And that should be good for defining our function here. So really quickly here, I'm going to reactivate this Qn, and we're going to use that here. Now, the way that solve IVP works is we need to have a function, a time span, a y value, choose our method, and for this one we're also going to have our dense output, and we're going to activate that to true. So first things first, our function is dHdt, right? Now our time span, we can go ahead, we'll create a variable here, and we'll call this tn. And for now, we'll set that equal to 3,000 seconds. That can be changed. And so we'll go 0 to t end, 0 to t end. We want a initial y value, so that's going to be our initial height. Height initial. We're going to set dense output to true. And the method we're going to use is the Radau method. The Radau method. Tn is not defined. I just need to do that. Okay, and that is how we use our solve IVP function. Now the next thing we want to go and do is going to use our subplots library to go ahead and graph out the simulation for us. So now we'll go ahead, we're going to name our tplot, and this is going to be using our np.linspace. And what we're essentially doing is we're creating time values to go ahead and plot with. So we're going to go from 0, time end, and we'll increment by 500 for now. Now we also want to go ahead, we're going to assign our height values using res.sol, and we're going to use our tplot values for that. Tplot. Now let's go ahead, we'll make our scatters. So we're going to go fig equals make subplot. And now we'll go fig.add scatter. Add scatter. Our x is going to be our times, so we'll go t plot. Our y is our heights, so for this one we'll go h1. We're going to name this tank 1. And we want the mode to be lines. Essentially, we're doing this the same thing, so I'm just going to copy paste this down and just change out the height and tank name. And 3, tank 3. Right? And you know what? Let's just see it. Let's see. What went wrong? Let's see what I did wrong here. So it turns out we can't have floats in our lens space. So let's see if that fixes it. And we can see that we start at our initial height, and eventually, over the time span of 3,000 seconds, our tanks eventually even out at this value here. Let's go fig.update layout. We're gonna go width equals 600. Height equals 800. Let's also change this to dark. I believe that's how you do that. We could change. Well, we don't need to do that. I shouldn't have these parentheses. Right? So we see the same thing. It's just evening out once we get to the top.